Right, it's past. I'd like to ask everyone just to make sure that they are muted and they've got their videos turned off. Right, everyone, I would like to welcome you to the 5th Zoom meeting of Cape Centre of the Astronomical Society of Southern Africa. For our long-time members, you guys know that we used to meet at the observatory, but we've made the decision during COVID-19 to rather stick to social distancing and have a once-a-month meeting via Zoom. So I would like to formally welcome all of our guests. I see that we have got a full audience tonight. I'm just seeing a bunch of names in front of me. And I would also like to welcome our Cape Centre members. I would specifically like to welcome 2 of our new members that have recently joined us. I would like to welcome Devin Detoy and Nadine Dempers. Devin, if I'm right, you guys moved on from Potchefstroom recently, and you now stay in Somerset West. Is that correct?
That is indeed correct.
Absolutely. All right. Well, welcome to Cape Centre, guys.
Thank you so much. Really appreciate it. I'm really looking forward to be a active member in this new community.
Yeah, I promise you, this is the place to be, and I'm really sad to say I hear you guys stay close to Martin Lyons, so you're going to be spending a lot of money there. My wife placed a restriction on me. I'm not allowed to come within 100 meters of his house.
I see Georg is here from Munich.
Is it?
Yes.
Welcome, Georg.
Hi, everybody.
Chris has given me a heads up that you're will be joining us, and it's a real privilege to have you on board.
Thanks so much for letting me in. Really looking forward to that.
Yeah, we've got a nice full audience tonight, and please enjoy the meeting with us.
Thanks so much.
Guys, I would just like to start off with a little bit of sad news. I was informed this afternoon by members of the astronomy fraternity of the passing of Dr. Japie van Zyl. So all of us that have got know who Dr. Japie van Zyl is, and he was of course heavily involved with the planetary exploration with NASA. And I understand that he suffered a heart attack 2 days ago, and that he passed away. And I'm not sure if he passed away this afternoon or this morning, but we would like to express our condolences to his family, and we really do keep her in our presence and in our hearts. It truly is a sad day for African astronomy. Because Dr. Japie van Zyl truly did put us on the map with all the different projects that he was busy with. We do keep them in our hearts and prayers. Right, I need to do one more bit of admin, and then I'm going to switch over to Dr. Michelle Lochner. I would just like to remind our regular members that our membership fees for the new year is payable. Please do an EFT or contact me or Willem to make arrangements if you're not able to do an EFT. Actually, there is one. Actually, sorry.
Could you remind us how much it is?
Right. So the membership fee for a single membership is 130 Rand. And for a family membership, it is 160 Rand. So that includes anyone living in your house with you. Because I had that in question, who does that family membership extend to? One last admin point that I just wanted to quickly discuss, and that is with regards to the SAO virtual symposium that is going to be happening in October. Cape Centre and ASA has been approached to assist with some of the lectures and workshops. So I would like to request if there's anyone here that is willing to maybe give a short lecture or present a short workshop during the symposium, please reach out either to me, to Chris, and to Christian, so that we can take this up with Dr. Daniel Kunema. Right. So let's switch over to the real purpose why we're here for the evening. Our guest speaker for tonight is Dr. Michelle Lochner. And Dr. Lochner, what I would like to do is, before we start off with your formal presentation, can you maybe just spend 1 minute telling us a little bit of yourself before I hand over the controls to you?
Sure. Thanks very much, Marius. And thank you to Ketchel for inviting me and to all of you for being here. It's definitely my first virtual public talk. There's some advantages in that I don't have to go anywhere, but it would certainly be much better to see you all in person. So I'm Dr. Michelle Lochner. I am a senior lecturer at the University of the Western Cape, but I also have a joint staff scientist appointment at the South African Radio Astronomy Observatory, which probably some of you will rather know as SKA South Africa. We changed our name somewhat recently. I'm born South African. I was born in Johannesburg, which is perhaps an odd place for an astronomer to be born, given that there's not that many stars. But nonetheless, I stuck it out and studied at Rhodes University and then got my PhD at the University of Cape Town. I did a 2-year postdoc at University College London before coming back to a permanent position in South Africa. And I moved to UWC in April this year amidst all of the COVID craziness. So my research focus is on mostly using artificial intelligence techniques in astronomy, and I'm going to be telling you a little bit more about that tonight.
Wonderful, thank you so much. Now that we know you a little bit better, I've handed you co-host control, and you may proceed, please.
Great. Okay, let's try sharing my screen. How does that look?
Perfect. We can see it.
All right. Can you see my mouse if I move it?
Yes, we can.
Fantastic. All right, so I'm going to take it away then. Okay, so I titled this talk, The Rise of the Machines in Our Quest to Understand the Universe. And so I'm going to be talking about artificial intelligence, specifically machine learning, and how this is helping us unlock the mysteries of the universe. But really, when creating this talk, I found myself wondering what many people are wondering right now, which is, am I still going to have a job in 10 years' time? So that's a fundamental question on my mind. So you may have heard the term machine learning, but probably for many of you, nobody's actually explained to you or tried to explain to you really what it is or give you an example of a machine learning algorithm. So I'm going to attempt to do that tonight. We're going to start at the beginning and ask the question, what is machine learning? Before I can get into machine learning, I want to try and disentangle two terms that are often used kind of synonymously, even though they're not the same. Everybody's heard the words artificial intelligence. And this has been sort of part of the makeup of sci-fi for many years. And in fact, it's a very broad field. So what is the difference between artificial intelligence and machine learning? Well, AI is much broader than machine learning. Machine learning is a branch of AI. In fact, AI is anything that is using a computer program to make decisions. So there's AI in your washing machine. It makes that on how much water to put in the washing machine based on things it can measure, like the weight of the laundry. So great. So believe it or not, there's AI in your washing machine, but it's pretty simple AI. It's not particularly intelligent artificial intelligence. And this is where machine learning comes in. So machine learning is a particular branch of AI where we get a computer program to try to learn without us explicitly telling it what to do. So most other branches of artificial intelligence, everything from washing machines to TVs to everything on an airplane is explicitly programmed. If this happens, do this. If you see this, that's this thing. Whereas machine learning tries to automatically learn an algorithm from data alone without us explicitly telling it what to do. Okay, so let's go through an example. So let's play a game. This is probably similar to a game that you might have played called 20 Questions. Imagine I'm thinking of an animal, and I want you to guess what animal I'm thinking of. And you're allowed to ask yes, no type questions, or questions with specific answers. So you might ask me, how many legs does this animal have? And I could say, well, it's got 4 legs. Then you might ask me, what color is this animal? I might tell you, it's gray. And then you ask the question, does it have fur? Depending on whether I say yes or no, you might think it's an elephant, or you might think it's a mouse. This very simple classification system is called a decision tree. And believe it or not, this is actually the basis for a very useful machine learning algorithm. So one of the typical problems that we want to solve with machine learning is classification. So for instance, if I was to give my algorithm lots of different images, I would want it to be able to automatically figure out what's in each image. So if I wanted it to know, to tell the difference between different types of animals, it would have to automatically figure out a way to do that. And one of the ways that you can solve this problem is with a decision tree, just like this one. Now, the machine learning part, the clever part, is that the algorithm itself is able to figure out this decision tree automatically. So I don't have to explicitly choose what the questions are. It will learn what they are from data. Okay, so you're looking at a basic, simple machine learning algorithm. So 3 things to keep in mind about this. We have to know what to ask the questions about before we could make this decision tree. And that means my algorithm has to know what it's allowed to ask questions about. It can't ask any infinite number of questions in the universe. It has to know what features the data might have. So in the example of animals, features would be things like numbers of legs, color, fur or no fur. Those were all features. So what we often have to do with machine learning is simplify the data down to sets of features that the algorithm can then digest and come up with this decision tree. There's a part where we have to figure out how to ask the questions. Now, when I initially raised the point, I'm thinking of an animal, ask me questions to try to guess what it is, you employed your machine learning algorithm, your brain, to think of what questions you might ask. So this is the actual machine learning part. It takes different features and tries lots of different types of questions it can ask, and then sees which ones work best. And the process required to figure out which one works best is called training. That's where I have to give it data for which I know the answer, so a bunch of examples of mice and examples of elephants. I tell it, these are mice, these are elephants, here's the features about them, go figure out the decision tree, and then off it goes. And automatically tries things until it figures out a really good decision tree that works well for this data set. A key point is that if we give the decision tree something it's never seen, it will give us the wrong answer. It's a little bit like if you have a child and they've learned to tell the difference between cats and dogs, and then you show them something like a tiger, the child will think, oh, okay, it's probably a cat. It sort of looks vaguely like cats, but it's never seen tigers before. You have to retrain the child's algorithm to include tigers so that it can learn to classify tigers. So these are the 3 main components of machine learning. We have to simplify the data into features. We have to use an algorithm to automatically figure out how to build this decision tree. That's the machine learning part. And we have to give it something so that it knows when it's doing a good job or not. And that's the training. So you have to have some data. But the cool part about this is, whilst this decision tree that I came up with was very simple, these algorithms can come up with extremely complicated decision trees that we humans wouldn't really be able to. So you can give it very difficult problems that it's able to solve that we wouldn't be able to design a decision tree that could solve it. And that's the power of machine learning. Okay, let's talk a little bit more about feature extraction, because this is actually a really important point that pretty much no talk on machine learning really goes into. So feature extraction, like I said, is a way of simplifying data down. So take, for example, a fingerprint. And fingerprint recognition has been around for many, many years. So this is a very well-solved problem. But if you look at a picture of a fingerprint, this is actually quite complicated data, right? There's a lot of pixels in there. It could be thousands of pixels in this image. That's a lot of data points. But what people figured out is it's only a few of those data points, called the minutia points, that actually matter. And so if you measure what the fingerprint's doing at the minutia points, you can build this map, which is a very simple representation of the fingerprint. And so you've taken a very complicated data set and simplified it down. And this is where domain knowledge comes in. This is where I hopefully still have a job, because as an astronomer, I know things about the data that help me to figure out how to simplify it down, in what way, what are useful features that the machine learning algorithm can then make use of. I want to just briefly mention neural networks. I'm not going to go in detail into these, but I thought I should mention it because for those of you who do know about machine learning or have read about it, you've no doubt heard this term. So neural networks actually could be argued as the oldest machine learning algorithm. It came about roughly 60s, 70s. And this was an algorithm based on how we think, or thought at the time, the human brain works, with these series of interconnected neurons. And it was really just a way of building up very nonlinear models, a bit like the decision tree, but just a different structure to it. And neural networks have recently, or over the last decade, had this incredible resurgence in popularity through the development of deep learning. So deep learning is a branch of machine learning where you basically build extremely deep neural networks. So you can see here, this is a very simple representation of a neural network, where you put in some data and you see the data is connected to all of these neurons, and the neurons are connected together to produce some output. Now, a deep neural network might have many layers of neurons, dozens, sometimes even hundreds of layers. So they're extremely complicated. They're very difficult to train. They require a lot of computing power, but they've been able to solve problems that have long been thought, well, not impossible, but were unsolved for decades in computer science. And really, I would say deep learning is responsible for this revolution, or one of the things that's responsible for this revolution that we're seeing in machine learning at the moment. So that's a whirlwind tour of what machine learning is, and I hope gives you a little bit of a slightly deeper insight as to what a machine learning algorithm actually is, and demystifying it a little bit. But the really cool part and the cool question is, what can machine learning do? So here's a simple example that's in your everyday life. So for those of you who've ever driven down the N2 and got a speeding fine in that stretch of road that has average speed trapping, that is made possible through machine learning, that there is a camera that can do license plate recognition. So this is an algorithm trained to recognize letters and numbers. And so it can snap a picture of your car, snap a picture of your car again at the other side, match the license plates and figure out whether you're speeding or not, and then you find a lovely speeding ticket in your post box a few months later. So this is something that's already in your everyday life. Now, there's machine learning actually all around with you. You're interacting with it every day, but you probably don't realize it. For instance, in a cell phone, there's a huge number of machine learning algorithms. If you go on any social media, Facebook, Twitter, if you use Gmail, if you browse on any website, there are machine learning algorithms tracking what you do and choosing to display certain content based on what it thinks you're going to like. Another example is Netflix or any streaming service. So machine learning is actually already in your life. You just may or may not realize it. But there's some less creepy applications that, well, they might still be creepy, but they're pretty cool. The one is image recognition. So this is one of the really big problems in computer science that people bash their heads against for decades. And it was solved by deep learning. And I would say image recognition is basically a solved problem now. So what happened was, it's also now about a decade ago, the ImageNet dataset was created, which contained millions of human labeled images. So some very conscientious people painstakingly labeled, yes, this is a picture of a house, and this is a picture of a dog, and this is a picture of the cityscape or whatever. And there was a competition for machine learning, or for any algorithms really, to try to solve this problem of image recognition. And the winner was a deep neural network. And this has advanced so much now that this is this is, I believe, a Google neural network, that there's one network that does the image recognition, so it tries to figure out, classify what's in this image. And then there's another algorithm connected to it that can write sentences. And so the two algorithms together decide this picture is of a construction worker in an orange safety vest is working on the road. That's pretty good. It's probably more detailed than I would say. I would be like, guy in an orange jacket. This one says 2 young girls are playing with Lego toy. It gets some things wrong. I'm not sure mom would like to be a young girl, or maybe she would. But you know, it's really incredibly good now. This is one of my favorite ones. Okay, if we were live in the audience, I would get people to vote, but I think this is tricky in the situation. So I'm gonna flash up a series of pictures. There'll be 2 images. One of them will have been a piece of art made by a human, and one is made by a machine learning algorithm that's been trained on abstract art. And very quickly, very instinctively, just to yourself, just think which one you think is real and which one you think is machine made. And then I'll go back and I'll tell you which is which. Okay, so here's the first one. So just to have a very quick look, instinctively, which one do you think is real? I'll go to the next one. Which one's real? Which one's, I don't even want to say fake, but machine made. And the last one, just very quickly, which one do you think? Okay, so the first ones, this one on the left, this is made by a human. This is drawn, you could say, by a machine learning algorithm. This one again is the one on the left. The one on the right is machine made. And here, the one on the right is human. This is machine made. So usually when I ask this, the audience is usually pretty much 50-50 on most of these images. Maybe there's a slight, 60% might get it right. So we already have computers that can create art that's more or less indistinguishable from humans. So it's an interesting question that creativity, I think, is something we've thought of as being quite human. But now this is an algorithm that's creating something. Is it truly creating something? I don't know. But philosophy aside, if you ask me which of these 2 pictures I would prefer to have hanging on my wall, I think I'm going to pick the machine. Anyway, that's just my opinion. Here's my last example. It's probably my favorite one. So there's also, it's my second last example. There's also algorithms that can write sentences. You already have it on your phone. If you use predictive text, it's using machine learning. So what this group did was they used a predictive text algorithm and they trained it on Harry Potter books. And so they didn't quite just let it write the whole thing, but they took the best sentences and they put it together into a kind of story. And I'm just going to read just the first bit because I think it's very funny. It's Harry Potter and the portrait of what looked like a large pile of ash. Chapter 13, the handsome one. The castle grounds snarled with a wave of magically magnified wind. The sky outside was a great black ceiling, which was full of blood. The only sounds drifting from Hagrid's huts were disdainful shrieks of his own furniture. Magic, it was something that Harry Potter thought was very good. I really recommend you look this up and read the whole thing because it had me in stitches. And there are many examples of this. There's even a screenplay that was written by an algorithm that was then filmed and turned into a short movie. And they're very funny because they're really quite bad at this point. But I would probably be willing to bet that within my lifetime, we will have algorithms that will be able to easily write books, screenplays, anything that will sound quite sensible and be a coherent story. They already can pretty much write news articles. A lot of news articles are written by algorithms. So again, this is, even though it has to be trained on something created by humans, it can still make something that's somewhat new. My last example is this amazing story about an algorithm called AlphaGo. I'm sure you know that it was many years ago that the first computer algorithm was made that could beat a human at chess. It turns out chess is actually a fairly easy one to solve because even though there's quite a lot of possibilities of the outcome of the game from any given position on the chessboard, there's not that many. It's still solvable, at least several moves into the future. So many chess algorithms are simple brute force algorithms. There's a game called Go, a very ancient Chinese game called Go. And this was thought to be that there would never be an algorithm that could beat a decent human player at Go. Because this game, for any given position on the board, there's an enormous number of possible outcomes. You cannot possibly brute force it. It's a game that's, they say, relies more on intuition than strategy. Intuition is another very human quality. So a few years ago, a company called DeepMind, which is now owned by Google, worked on a deep learning algorithm to beat human players at Go. That was their aim. And there's a beautiful documentary on Netflix if you're interested in watching it. And they film AlphaGo beating one of the best Go players in the world 3-2 in a round of matches. And it's amazing, in the beginning he thought, oh, it's impossible, this algorithm will never beat me. And then of course it happened. And there's a moment in the documentary where the commentators are watching this game and the algorithm makes this move and they look at this and they're like, why would it do this? This is a stupid, crazy thing to do. No human would make a move like this. And of course the algorithm won that game. And then they went back, they said that was the move. That was the definitive move that made it win. So it did something that no human would do and it resulted in winning the game. So it's an interesting question of what kind of regions of possibility are we not exploring that could then be explored by machine learning algorithms. Okay, so hopefully I've either wowed you or terrified you into the possibilities of machine learning. So let's take a step away from machine learning, go into astronomy, and then we're going to put the pieces together at the end. So let's talk about astronomy. I don't have to tell you all about how amazing astronomy is. What I do want to tell you about is the two new telescopes that I'm most excited about. I'm going to start with optical astronomy. We've come a long way from Galileo and his little telescope. And I think, as you all know, bigger is better with telescopes, and we really are in this golden age of enormous telescopes and an enormous amount of data. The one I'm particularly excited about is called the Vera C Rubin Observatory. Some of you may have heard of it as LSST. It recently changed its name. So it's now the Vera C Rubin Observatory. This is a telescope that's under construction in Chile. It's a US-led project, but South Africa is involved. I'm one of the people involved in the project. And this is really an amazing telescope for many reasons. that one of the main ones is that it's an 8.4 meter diameter telescope. So you know, bigger is better in astronomy. The bigger the diameter, the more collecting power you have and the more resolution you get. But there's something a bit magical about Rubin. If you compare it with Gemini, which is a similar size, Gemini's got a very small field of view. Rubin's got clever optics and a really, really big camera on it, which means it's got a field of view that is 3.5 degrees across. So you could fit 7 full moons across this field of view. So what this means is that this telescope can observe most of the southern sky every 3 nights, and to quite an incredible depth. So it's really the telescope that can kind of do everything. So these are just a few pictures of the construction. This is the oversized load of the mirror being moved to Chile. Obviously, construction's halted at the moment because of our dear friend COVID. So first light's delayed. It's probably going to be something like 2023. This is another reason to be excited that Rubin will have the biggest camera in the world. It's actually just finished. This is an old picture. This gives you an idea of how big it is. It's something like 4 gigapixels. It sort of starts being meaningless at this point. But this is one of the reasons it's able to see such a huge field of view. So we have this huge field of view, huge camera, huge mirror. What does that mean? It means science. So what is the science that Rubin's going to do? With one survey, they've renamed the survey to LSST. It's the Legacy Survey of Space and Time, which is quite corny. You should never let astronomers name anything, but there we are. So the survey is going to attempt to do all different kinds of sciences with a single survey, which is quite rare. So it's doing everything from solar system, particularly looking out for near-Earth asteroids. It's going to do the transient sky, because now we're effectively making a movie of the sky, right? Viewing the whole sky every 3 days, we can see everything that changes. And I'll talk a little bit about these in a minute. It's going to look at the Milky Way in exquisite detail, so we're going to learn a lot more about our galaxy. And of course, it's going to do my favorite, which is cosmology. And that's trying to understand the structure and evolution of the universe. So it's really going to do everything with this one incredible survey. So this is the one telescope I want you to keep in mind. We're going to come back to it a little bit later. And it's the big data experiment that I'm really excited about. The other one I'm excited about is in radio astronomy. So radio astronomy is different from optical astronomy in the sense that we look at the sky in the radio part of the electromagnetic spectrum. This picture gives you an idea of the kind of typical scales of the wavelength of light that we normally see here. Radio is much longer wavelength. So the telescopes really do look quite different. In fact, they look a bit like your old DSTV satellite dishes. One second. So they look a bit funny, but they do a great job at looking at the universe in the radio. So why would you care about radio astronomy? I mean, you guys have probably had plenty of talks on the SKA, so I probably don't need to convince you. But just in case you haven't, here is a beautiful picture of a set of 3 galaxies in the optical that look like they don't have anything to do with each other, right? When you look in the radio, you're sensitive to all the hydrogen gas, and then you see that there's actually a huge amount of interaction going on. It's like they're involved in this cosmic dance that would just be invisible if you only looked in the optical. So the radio sky looks quite different from the optical sky. We get a lot of information from it. Radio astronomy has also come a long way from bits of wire stuck in the ground to much more sophisticated looking instruments that look like this. So this, again, I'm sure many of you have seen pictures. This is the MeerKAT telescope out in the Karoo in South Africa. So MeerKAT is a precursor, I'm going to talk about it in a second. It's a precursor to the Square Kilometre Array. So SKA, once it's built, will be the biggest telescope in the world. the eventual aim is to have a collecting area of 1 square kilometer, which is really, really big. So you would need thousands of these dishes, as well as millions actually of these really small antennas in the low frequency part. But anyway, we're working our way up to that. And South Africa is co-hosting the SKA with Australia. So we'll get the part of the telescope that looks like this, made up of these dishes. And the first phase of the SKA is a few hundred of these dishes. So it's still quite substantial. But until the SKA comes along, it hasn't really started construction yet. But we have this really beautiful telescope called MeerKAT. So MeerKAT is a precursor, or Pathfinder, it's also called, telescope. It's made up of 64 of these beautiful dishes, and it's out about 90 kilometers away from Carnarvon, which is a small town in the Karoo. And it's really quite an incredible instrument. It was designed and built by South Africans, and there's a lot of South African scientists using the data from it. And it's actually, in its own right, a world-leading telescope. It's really one of the best in the world. Just to prove that to you, this is the image that MeerKAT was inaugurated with of the Milky Way. And you can see that the Milky Way looks quite different in the radio because we're not obscured by all the dust that is obscured in optical. And we can see a lot of the activity going on in the supermassive black hole in the center, somewhere in here. And this is the most detailed view of the Milky Way that we've ever had. So this is an incredible telescope. So let's just keep in mind those two telescopes. There's a Vera C Rubin Observatory in the optical, and then there's MeerKAT, and later on SKA in the radio. And I just want to point out that both of these telescopes are really pushing the limits in terms of the amount of data that we are dealing with. And that is where I come in with machine learning. Okay, so this last part is putting the pieces together, machine learning the universe. So let's first talk again about Rubin. So as I said, Rubin Observatory is going to basically make a movie of the southern sky. So here's a simulation of what it might look like. Every single one of these dots is a supernova. That is the death of a massive star. And up till now, we've found a few thousand of these things in sort of the whole history of humanity. Rubin will easily surpass that in just the first year of surveying, right? So every single night, we're going to see a whole lot of these supernovae. So what is a supernova? The supernova is the dramatic death of a star. So a star much bigger than our sun eventually runs out of fuel and collapses in on itself in this really gigantic, gorgeous explosion that we see from many light years away. And they're a very exciting and useful tool for cosmology. So they're really one of the most studied objects in the universe. But they're not the only thing going bump in the night. There are also things like X-ray binaries, which is black holes or neutron stars absorbing matter off of their companions. There are active galactic nuclei, which I've heard beautifully described as galaxies behaving badly. So that's where the supermassive black hole in the center of the galaxy is very active and absorbing lots of material and emitting these jets. So there's a lot of transients in the night sky. We call them transients because their brightness is changing. And the Rubin Observatory is like a transient machine. It's just going to be so, because of the big field of view, the depth, and the fact that it can observe so quickly, it's just going to find so many of these. So I like to ask this question: how many of these exploding events or transient events is Rubin going to detect in a night? Just think about it for a second to yourself. Well, the number is 10 million every single night. Every single night, 10 million times a night, something in the sky is going to change. Now, half of that is going to be junk, cosmic rays, airplanes, a whole lot of it's going to be satellites. But that still leaves, 5 million potentially interesting astrophysical objects. Now, the problem is these all look fairly similar, right? It all kind of looks like it's dark and then it goes bright. And there's just not enough grad students in the world to sit and go through all this data and manually classify every object as a supernova or an X-ray binary or a variable star or a whatever. So machine learning has to play a vital role here and is an extremely active field of research. So this is something I've worked a lot on. If you take a supernova and you look at this image of a galaxy, so the supernova is over here, and then you watch it get brighter and slowly fade away, and you draw a curve of that, it will look something like this. Now, it's difficult to tell apart the different types of supernovae. Normally, we would do what's called taking a spectrum, which is much harder to do, and we won't be able to do for almost all of them. But there are subtle differences between the light curves of the different types. And so what we did is we took a whole lot of data. We did our good old feature extraction that I talked about right in the beginning. And we trained a machine learning algorithm to try to tell the difference between the different types of supernovae. And I would not say that this is a solved problem. This is still a very difficult problem, but it's clear that the only way to do this is with machine learning, and it's a very powerful tool. So let's talk about the SKA. The SKA, the data rates start getting stupid. We're talking about 100 petabytes of raw data every day. It's beyond anything we know how to deal with. And there are interesting questions that we want to know. For instance, these active galaxies behaving badly, they're really useful to study in the radio. That's where we see these powerful jets and we learn so much about them. Here's an example. I'm sure all of you remember, I think it was last year, the Event Horizon Telescope taking the first ever picture of a black hole. And this is the supermassive black hole at the center of our galaxy. So this is something we really care about, and something that MeerKAT is beautifully good at. So this is an image. This is a image made from MeerKAT data. So you're looking at the radio sky. You're seeing what it looks like. And now this is just one image. That's okay. That's easy to deal with. You can manually go through this image and see what's in it. Oh, look, there's this radio galaxy here. Here's the spiral galaxy. Easy enough. But even MeerKAT can produce about 1 terabyte of images every day. And it's just it's a shame if we don't try and explore and exploit this data. So if I have an image like this and I just want to find interesting things, how would I do it? So the question that's been on my mind for the last year or so has been, how are we actually going to do scientific discovery in this era where there's just no hope of manually looking at all of the data? And there's a long history of amazing discoveries of astronomical phenomena. Sometimes we're expecting it, like with gravitational waves, we were looking for them. Sometimes, like with pulsars, they were completely unexpected. And the only way they were discovered was when a human being looked at the data and went, this is odd. How are we going to do that when we have no hope of looking at all of the data? And so I'm interested in using machine learning for what's called anomaly detection. So as a trial, I took this image from MeerKAT and I just chopped it up into these little boxes. And I trained a machine learning algorithm, and instead of asking it to tell the difference between elephants and mice, I asked it to just show me what looks weird. Which box looks the least like all the other boxes? Okay, so each of these boxes contains a part of the data. Most of them look like this. These funny little squiggles you're seeing, that's just noise. These little dots, those are point sources. Those are probably radio galaxies. But they're unresolved. I can't do anything with them. These are the kinds of things that I'm interested in. This is a radio galaxy doing something a bit odd. So again, I take these images, I reduce them down to a set of features, and now this time I run my algorithm and I ask it to tell me what looks odd. And so if you look at each dot in this is just a representation of the data, but each dot represents one of those little cutouts. And all the ones in the middle, all the kind of normal ones, are things that are just noise or a point source. But the ones that are on the edge look a little bit interesting, a little bit different. Here's an active galaxy that's probably interacting so much with the galactic medium, it's flipped one of its jets over. This is a FR2 radio galaxy. This is actually spiral galaxies are quite rare in the radio. They don't emit very much, so we don't see very many of them. And this is a beautiful active galaxy that is definitely interacting in some sort of unusual way. Same with this one. So what I was able to do in just a couple of minutes, instead of laboriously having to go through this whole image, is quickly pick out the objects that look interesting, look different. Now, this is not to say these are things that we've never seen before, although because MeerKAT is so sensitive, quite often we haven't seen things behaving exactly like this before. But the point is that if you start having a large number of images, a large data set, you'll be able to really quickly pick out things that might be interesting. Okay, so that's the whirlwind tour of machine learning, astronomy, and putting the two pieces together. So the final question is, what's the future? Am I going to have a job in 10 years? Or any of us? So when you talk about machine learning, some people are afraid. You know, we think of Terminator or these robots in Israel that can automatically fire people, or the Cambridge Analytica scandal. And, you know, there are many reasons to be afraid, many good reasons. Some people, especially when you talk about machine learning and science, less and less these days, but some people are still very dismissive. They don't think it's really useful at all. And I think when they think of machine learning, you know, they think of this great video from Boston Dynamics of a robot trying to be like a human and really failing quite miserably at it. But then there are some people like myself who are excited. And I see machine learning as this useful tool that's really going to help us push the boundaries of what we can currently do in astronomy. And I hope will enable some amazing scientific discoveries that might not be possible otherwise. So do I think I'm still going to have a job in 10 years? Pretty sure, but I'm also pretty sure a lot of that job is going to involve machine learning. So I'll finish off by saying the future of astronomy is here. It looks very good, and I'm personally very excited. Thank you very much.
Hi, Michelle. Thank you very much for an absolutely fantastic presentation. Let me just quickly do my bit of admin from my side. And there we go.
Should I stop sharing or should I?
It doesn't matter. You can keep it going. After I've withdrawn the sharing host, so it should stop. Let's just quickly have a quick look. There we go. Thank you so much. Wow, that was a really awesome presentation. What I would like to, first of all, just say thank you so much for taking the time out to come and share your wonderful knowledge with us. For me, as a person that's been in the IT industry for a good couple of years, I found this really fascinating and really interesting, and I've got a couple of questions. But I would really like to open up the rest of the floor to a Q&A session. But I would just like to maybe just jump the gun a little bit. I mean, we're looking at machine learning. Machine learning has been something, you know, as you said, you know, in the past 10 years, it's really been on a steep curve, on the uprise, but sort of walking hand in hand with that, it's been quantum it's been quantum superposition. We've got quantum computing, that's got the ability to take machine learning up to an absolute next level. I mean, we were looking at the amounts of data that's being produced, 100 petabytes a day. I don't know how many people in this audience really understand, how much 100 petabytes is. And I think it's even sort of above my understanding of, I was looking at terabyte databases a couple of years ago, and I really thought that was huge. And now we're talking about 100 petabytes a day, which is something completely different. But, being able to work through that type of information, even with a normal, what was considered a supercomputer, was nearly an impossible task. Now comes the age of quantum computing. So that was really opened up a really wide field for people that is playing in the machine learning field.
Yeah, absolutely. Yeah, I mean, I think computing has actually stagnated for many years. We've hit the limit of Moore's law. So I'm sure those of you in IT will have noticed that it's just stagnated. The speed of computing hasn't increased. We've reached a quantum limit of how close we can stick, how many transistors we can stick in a chip, basically. So there has to be a kind of step change in how computing changes if we want to be able to keep up with analyzing this amount of data. I think quantum computing, it's super exciting. It's still in its infancy, particularly because you basically have to redesign your algorithms to get them to work on a quantum computer. And this has been done for some things, but certainly not for everything. So it really is a very different approach to computing. But I think it's very exciting, and I think it's a very viable future. For something like the SKA, talk about storing 100 petabytes a day, you just can't. I mean, we would fill all the servers in the world. So it has to be analyzed on the fly and processed on the fly. And I think the majority of the investment that goes into the SKA is going to be in computing. We really need a large supercomputer. I mean, MeerKAT has a pretty large supercomputer on site that processes information as it comes off the telescope. And that's just doing the initial part of the processing. Then it gets streamed to Cape Town to do the rest of the processing. And for the SKA, that whole process has to be streamlined and improved, and you really just have to throw a lot of computing at it. It's an incredibly difficult challenge. We're not 100% sure. I mean, we haven't solved it yet, but we're fairly confident we will.
Wonderful. Well, thank you so much for expanding on that point. We've got our first question. That is from Kevin here in Cape Town. So Kevin, you can unmute yourself and you can ask your question.
Thank you very much, Maurice. Michelle, wow, I've been in IT since the mid-'80s, and I'll tell you what, I was blown away, especially when the last bit about the 100 petabytes came in. I thought I've got quite a good grasp of numbers and sizes, but that's just, that's in another league. A quick question, but maybe not such a quick answer, but just something that went through my mind. I studied maths at university. I did my major in maths, and if we take X amount of data, let's just say a petabyte, and let's say that in half an hour, which is what you need while the data is streaming in, my question is, do you know, not you, but the people who are involved in these projects, data scientists, astronomers, do they know what fraction of data that they are currently looking at, let's say in 1 petabyte, that they would really need to analyze seriously in order to extract what they need to get? In other words, the question really is, if you know anything about image processing, and I'm sure you do, like, for example, if your image is composed of gray going all the way to blue, but with a hard line in between, if you could detect that hard blue line, you wouldn't need to worry about the rest. You detect the division of the line. Yeah. I don't think that, there is actually a determination, but you might prove wrong, because I think it's a question of how much you want to get out. Would you need to literally go through each byte in that petabyte? Because if that's the case, then there's a huge problem with what we might miss. Over to you.
That's a great question. And this is actually something quite specific to radio astronomy. So even though we might be looking at the same sky, The SKA produces much larger data sets than something like the Rubin Observatory. And that's got to do with the fact that it's made up of these hundreds of different antennas that we need to basically put the pieces together in order to get out an image. That final image that I showed you of the MeerKAT data that I was looking for anomalies, that's about 200 megabytes. The data set that they came from might be a terabyte big. So the point is the raw data is highly uncompressed and quite redundant. So it can be compressed down much, much smaller. The problem is it's actually what's called an ill-posed problem to actually create that image. There's not a unique way to make an image. You have to make a bunch of choices to get it. And so the scientists don't like this. We want to keep all the raw data because, you know, maybe Fred wants to analyze it in a different way from the way I'm analyzing it, but we can't. We have to build a standard pipeline to get out those images to be able to do that data. And a lot of people are working on different ways of compressing the data. So this is definitely being looked at in different angles, but for sure, we don't need to keep all of it. We sort of know how much we do need to keep and what parts we need to keep, but it's still an active field of research.
So yeah, thank you very much. So just to get back, I do astrophotography part-time. Well, actually, you know, I'm pretty serious about it. I've been doing it for about 10 years. And as you know, in an image, there's so much noise that the amount of, you know, if you take even a galaxy, you put a tiny galaxy, pinwheel galaxy in the middle of your image, probably it only takes up the data, I don't know, if you look at the histogram, you know, let's just say 5% or even 1% or 10%. So that 100 petabytes, is it possible that if we get our processes streamlined enough, our mathematics, our data science, that we could take the meaningful data in there with our current knowledge of what we want to find down to, say, orders of magnitude less?
Yeah, and that's exactly what we do. Yeah, that is exactly what we do when creating an image. And I mean, the other thing to remember is that the raw radio data is in a very different form. We're correlating voltages from the telescopes and we build this gigantic matrix out of it. So the actual format of the data is quite different. But yeah, so there's two levels of that. And then also that you're talking about background noise. But don't forget that as we go deeper and deeper and deeper, stuff that appears as background noise actually resolves into galaxies as we're able to reduce the noise level of the telescope as we integrate longer. And when you look at an image like an average, like a deep MeerKAT image, there's a lot of galaxies in there. You'll be hard pressed to find an empty patch.
Yeah, that's true. Going down to Mach 20. And last things, do you think that even though these data scientists are concerned that, you know, in the initial maybe years that the data streaming, they're missing out things, remember, the machine might also be able to learn and say, hey, in future, we mustn't lose that data. We must keep that data and get rid of that data. We've seen enough about type 1a supernovas. We were more interested in gravitational lensing. You know, so I think there's a lot there that even starts to go into the philosophical side. You know, it's very deep on some level. Very interesting. Thank you very much.
Thanks, Kevin.
Thank you so much, Kevin, for your valuable input there. All right, so let's open up the questions to the rest of the floor. Anyone want to ask Dr. Michelle another question? Hi, Devin. You may unmute yourself and ask your question.
Hey, can you hear me?
Yes, we can.
Hello. Perfect. Okay. Hi, Doc. How are you? Very interesting talk. If you wouldn't mind, I'd just like to actually look at your slide regarding the your data points captures. I didn't see what type of framework did you use to sift through the data. Was it perhaps a well-known one as an open source? I'd really like to look at the engine of your system that you're using.
Sure. I think I can't share my screen again.
I have shared. I've made
Oh,
the closed again.
there we go. There we go. Okay. Were you asking about the, could be a little tricky to go that way.
So
about the anomaly detection?
There was, yes, at the anomaly detection. I can't remember what the graph was exactly, but I think I saw you labeled it something. But just for clarity, I believe, yeah, this is, no, yes, this is this one. So to analyze the data, what frameworks did you use?
Okay, I can quickly show you. So I built a piece of code called Astronomy. It's publicly available on GitHub, and the paper is coming out quite soon. So if you use Python, it all runs on Python, and you can even run it on like a data set of JPEGs, for instance, if you're interested in that. But yeah, so the code, hang on, I'll just copy paste this in the chat, which I can't get to right now. Okay, in a minute, I'll copy paste it into the chat. So yeah, it's basically, it's a framework that I built that uses a whole lot of existing tools and some tools that I wrote myself, which is able to do anomaly detection for a variety of different data types.
Lovely. Tell me, sorry, just to build on that question, are you planning on expanding this in the open source environments, or is it a closed case that you'd like to?
It's all open source. It's going to be a license.
I'll
Yeah.
definitely have a look at that. Thank you so much.
It's a pleasure.
Thank you, Devin. Devin, maybe later on you can expand on why you're interested in that field.
Well, sure. Just to give a quick.
I would maybe just add the caveat that it's designed for scientists, which is not meant to put anyone off, but you would definitely need a bit of coding to be able to get it to work. So
Yes,
if you, I've tried to make it pretty easy to use, and although there's very little documentation, I think it should be easy enough to get started. But yeah, you will need a little bit of Python to be able to get going.
Yeah, okay, no, most definitely. The reason I'm actually asking is I'm doing quantum computing and looking for some algorithms to apply within the field of quantum informatics. And one of the next algorithms I'm actually looking at is the quantum machine learning algorithm. So just to perhaps find some cases where I can apply it within a more, I don't know, practical sense, you know, not just the more theoretical or lack of better word, I can't find my words now, but yeah, you get what I'm trying to say, just looking at some cases where I can perhaps apply it. So if I could, you know, just apply a front end, you know, clear some data within an algorithm, perhaps that would clear it up a bit, but you know, this is all just speculation at this point.
Yeah, that sounds great. I mean, feel free to drop me an email. I think I'll just put my email in the chat as well if you want to chat about it. It sounds really interesting.
Yes, definitely will. Thank you.
Cool. Thank you, Devin. All right. The floor is open. Richard, how are you keeping?
Oh, unmute. Am I unmuted now?
You are unmuted. We can hear you, Richard.
Okay, great. Thanks very much, Doctor. That was a very nice talk. What I want to ask you is that, is it necessary once the system is up and running to recalibrate it every now and again? In other words, do you give it tens or hundreds of scenarios, see what analysis it does, and then give those same tens or hundreds of scenarios to a few hundred humans and see if they all get the same answer?
That's a great question. And in fact, it's something I didn't touch on, but is actually an integral part of the anomaly detection framework that I built. Because the problem is, you know, the computer is actually still pretty dumb. So for instance, in the case of anomaly detection, a satellite streaking through an image will look anomalous. It doesn't look like anything else in the data, but I don't care about satellites. I don't want to know about it. So there has to be what's called human in the loop learning. So this is a big focus of my research at the moment, is basically how to combine the power of the brute force of the machine learning with the intuition and scientific knowledge of the human. So what my framework has is that a human can look at a set of objects that have been ranked by anomaly scores. So the computer's like, look, I think these ones are the weirdest things that I've seen. And a human can go through and give them labels and say, yes, that's interesting. No, that's not interesting. Yes, that's interesting. Go, 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 go. And then it can retrain it. So there's another layer of machine learning that happens on top of that. And then it effectively builds what's called a recommendation engine. So I don't know if you've ever used Netflix or any of these streaming services or done online shopping or anything where it says, we think you'll like this, right? That's called a recommendation engine. And basically what this is trying to learn what the user's interested in. And so the same thing will happen here with the anomaly detection, that the user can label these objects, and you can very quickly label even a few hundred objects, but it's better than going through 60,000. And then retrain the algorithm to make it better at giving you the things that you're interested in. But there's an important part of it where it still will display stuff that you've never seen before. So if it doesn't know, if it's nothing like anything that's been labeled, it's still going to show it to you, so you don't miss anything, if you see what I'm saying. So yes, basically all of these algorithms, even the classification algorithms that are running along nicely, as soon as you get a new telescope and you go deeper, or the data changes in some way, or as we add more data, we're always retraining these algorithms. And there's definitely a place for, there's always going to be a need for some human intervention, some human training. But definitely the way I envision the use of this anomaly detection system is in a kind of online mode where you're continuously able to label data and keep improving the algorithm.
Okay, great. Thanks a lot.
Thank you so much, Michelle, for clarifying that for us. Right, so who's next? Anyone got any more questions? I'm just looking for our list here to see if anyone's put up their hand. Rudolph, yes. Your question, please.
Sorry, I forgot I was muted. Thank you very, Doctor, for this for the talk. It was very informative. In your work so far, have you ever worked with real data, as in, let's call it real-time data, and found anything of interest?
Yes and no. So I've been working with some new MeerKAT data, it's not public yet, and spotted this really, I wish I could show it to you, it's this really beautiful pair of active galaxies. We call them the kissing tailed galaxies because they're both bent almost, it makes almost like an X shape, and they're almost touching. We don't know yet if it's just a coincidental alignment or if they're actually interacting in some interesting ways. So I do think some of the things that we found are interesting or potentially interesting, and now we're in the process of doing the follow-up and trying to figure out what they actually are. The other thing that we found is I worked with a student in the States, and she has a data set. So as well as working in images, I've also been working on transients. If you remember, I talked about these are objects that change in brightness. And so she had a data set of about 65,000 of these things, and she didn't know how to analyze them. So we worked with them with Astronomy. She found nothing particularly exciting, but one was called an ultra-fast flare star. So flare stars are basically very mature stars near the end of their lives that are quite unstable and do quite weird things. And in this case, so you get these big, effectively the same as a solar flare, just big ones. And so she found one that was just quite unusual, much faster than any that we've seen before. So you know, I haven't found anything Nobel Prize worthy yet, but certainly found a few things that were interesting. And you know, we've only just started, and there's tons of data out there that we're busy playing with. So yeah, and I basically only worked with real data, so I haven't, yeah. So I was busy exploring some interesting data sets now.
Well, that is good news, definitely, because then it's working as intended.
Exactly, I do. I mean, there's always plenty of room for improvement, and you know, with each data set, we're finding ways to improve the algorithm. It's definitely not finished, but yeah, it's working as intended. We are finding things.
And then for how long will these data sets be stored? Obviously, we're talking about the petabyte region. We can't keep these data sets around indefinitely, but obviously, as the algorithm, let's say, gets smarter, you can always go back and sift through the old data to get even more results.
Yeah. So for MeerKAT, it's still feasible to store the raw data. So remember, the raw data is in a very different format from those final images, much, much bigger. So MeerKAT stores the raw data for 6 months. And then it's up to whoever's data it is to get the data off the system and process it themselves. And then it gets deleted. But the processed images will be stored, can be stored pretty much indefinitely because they are so much smaller. For the SKA, we have to process it on the fly. It's just impossible to store that amount of data. So, you know, there'll also be a similar kind of buffer and it will get processed. But those final products, those final images are not, you know, they'll be sort of the order of terabytes to maybe a petabyte in size for a big survey. So those we can store, and those are what I operate on. So there'll always be, as the algorithm improves, there's opportunities to go back and look for things. And particularly if you find something weird, one of the first things you might want to do is go and see if you find any more of the weird thing. So you would then want to train the algorithm to specifically look for that.
All right, awesome. Thank you very much, Doctor.
Thank you for your question, Rudolph. I'm looking for the list to see if anyone else has put up their hand. If you don't want to put up your hand and just want to ask a question, you're welcome to unmute yourself and ask the question as well. So let's give it a...
I just would like to ask a question. So I'm a final year student in Vera C Physics at WC. I'm looking forward to study cosmology and in the NAS program next year. I'm really interested in cosmology, and so is mathematics. I think that's my strong point. But what if I want to focus on computationally doing things in cosmology further? I don't have a very strong background in computer science, but if so, are they going to prepare me in cosmology for computationally knowing things and doing other languages? Because I only know Python and a little bit of Java. So is there a possibility for me going into this type of thing?
It's absolutely is a possibility for you. So first of all, don't worry, because I'm taking over your computational physics module this year. So when I'm done with you, you'll be super confident in programming. But, you know, in NASP, in my honors year, most of the students hadn't done any programming. So this is now 10 years ago, but, you know, it was still the case then that most hadn't really encountered much programming. They gave them like a crash course in Python and were like, well, good luck. The great thing about programming is it's one of the most important skills you could possibly learn, but it's also one of the easiest skills to teach yourself because there are so many resources online. You know, it's actually quite hard to teach. If you was like, I'm going to learn fundamental physics, it's not that easy to do that just with online resources. But because so many people want to learn programming, there's a ton of resources available online. And so this is something that you can definitely work on yourself and improve yourself. And the best way to learn programming is with lots of practice. And when you get into doing cosmology and when you start doing a really computation heavy project, you'll learn because you'll practice it a lot and you'll get better at it. So there's plenty of opportunity. Don't stress.
Thank you so much.
Thank you so much for your question, Ron. Kevin, I see you've got your hand up.
Hi, I'm back to annoy you, Doctor. Just a quickie, yeah, carrying on from the last gentleman, it actually came to my mind. Obviously, these projects are, you know, subdivided into different departments and different expertise. But I'm just curious. It would be very difficult to get a specialist, a PhD in, you know, cosmologist with a specialty PhD, who's also a data scientist, who's also a neural network specialist, who's also a machine code learner. Do you find that most people you're working with in this area have got quite a lot of everything but are specialists, or are they specifically looking for certain types of people? In other words, just a data scientist with 10 years experience, just a Python programmer, just a cosmologist, or does it tend to be people who've involved, you know, in technology, but with one particular strong point?
Yeah, that's a good question. So, I mean, like For myself, I think I'm one of these a bit of everything type people, you know, do some astronomy, do some radio, optical, machine learning, statistics, blah, 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 blah. And I think it's not that common. It's becoming more common, but it's not that common for scientists to be that broad. I think what's happening a lot is you're seeing more and more people like me who are interested in methodology, you know, who are working with the more specialist scientists. So in the case, for instance, with the MeerKAT data, you know, if I find a weird looking radio galaxy, I don't really know what it is. So I go to my colleagues who are specialists and I say, what does this look like to you? So there are people like me who do a bit more methodology and a bit more of the kind of glue between the, you know, with working with those more specialists. And I think what you're starting to see more and more is people bringing in actual computer scientists into groups to work on dedicated software projects, because astronomy is becoming more and more software heavy, and scientists are usually not that great at writing software. So they'll bring in more computer science people to write dedicated pieces of code that are usually much better than the stuff we hack out. That being said, I did try really hard with astronomy to make it a bit more professional. But yeah, so I think we are starting to see a combination of people who are fairly broad, but also teams of specialists in different things.
Collaboration.
Together.
Like collaboration, yes. Which obviously strengthens it. Instead of just having a bunch of 5 cosmologists, so we might be able to look at an image and find everything in it, but only about cosmology. They might miss asteroids, they might miss, you know, something that isn't in their field. So and
it's an interesting time of becoming, you know, everybody's getting more and more specialized, but at the same time, there's more and more need for interdisciplinary work. So there's this place for more broad kind of people.
Very exciting, very exciting, very exciting. Thank you. Thank you.
Pleasure.
Kevin, thank you so much for your question. Richard, I see you've got your hand up.
Yeah, please. I know I asked a similar question of last month's speaker, but with regard to the Rubin telescope, are there any latest updates on efforts to mitigate the interference by the Starlink constellations?
Yeah, that's a great question. I could go on a rant for an hour about Starlink. For those of you who may not be aware of it, these mega constellations of low Earth orbit satellites, the first set of which have been launched already. This is Elon Musk thing called Starlink. The idea is kind of providing internet to anyone in the world. It sounds great in principle, but is, I think, a terrible idea. Mega constellations are extremely bad for astronomy. In particular, these low Earth orbit satellites are really bad for science cases that require twilight observations. So this is, you know, just as the sun sets, the sun is still hitting these low Earth orbit satellites, so they're extremely bright. So, you know, Rubin is $1 billion telescope, and one of its main goals is to spot asteroids that could potentially kill us all, and it can't do it with all these satellites in the sky. So there's been a lot of work, and actually I was just today reading an interesting report. I'll see if maybe I can find the link and whatever. But anyway, there's an interesting report from a team of people after a workshop. I think they called it SatCon, bringing together astronomers, engineers, and these commercial satellites operators to try to figure out how to deal with this problem. So it's always going to be a problem. The more satellites you put up there, the worse it is for astronomy. But there's still stuff that, you know, knowing that commercialism will not be stopped, these satellites are going up there. So there are things that you can do to mitigate it. And that's stuff like, you know, they're talking about painting them a kind of matte black color so that they reflect less, restricting levels of orbits, because if they go, the higher they go, the later into the night they cause a problem. Things like sharing with us the exact paths of all the satellites, which makes it a bit easier for us to kind of excise them from the images. For Rubin, it's a problem because it's a very big field of view, so you're always going to catch satellites. There's going to be satellites in most of the images, something like 40% of the images. The good thing is, though, that they are, if you don't worry about the twilight observations are really bad, but the rest of the night observations aren't too bad, because they'll make these streaks on images, and we do know how to excise them and just get rid of those pixels so that they don't interfere too much with the rest of the image. And they're also easy to, using, again, machine learning, it's very easy to tell what's a satellite and what's something else. So in that regard, we will probably be able to deal with it, but we are going to lose a fair amount of data because of them.
Okay, is anybody thinking of taking any kind of legal action?
It's really hard because nobody owns space. It's international. The same government that is paying $1 billion for the Rubin Observatory also allowed these satellites to be launched in the first place. This is the US government. So so legal action, not really, but kind of societal action is what astronomers have been doing, and we've been very vocal. And because it's not just about astronomy, it's also about the fact that this is our sky. The sky belongs to everyone on Earth, and it's being irrevocably altered from these satellites. So it's more of a societal kind of protest that I think is happening. Legally, it's difficult to, I think this needs some kind of new international treaty that might come about, but it's not really clear what direction this is going in. I think astronomers are trying really hard to work with satellite operators rather than just crying about it, to try and find ways to mitigate it. But I think this is a really, really serious problem.
Thank you for your question, Richard. I see that Hasip's also got his hand up. Hasip, thank you so much. Please ask your question.
Hi, good evening, everybody. Hope you all can hear me. Good evening, Doctor. I am actually going to study astronomy. And I want to know, is it better for me to apply at UWC to do the undergraduate degree in a natural science such as physics, or go through UNISA to do the undergraduate degree in astronomy?
The answer to that question really depends on more about your personal circumstances, which, I obviously don't know anything about. I'm completely biased because I'm at UWC, so I'll say, oh no, come here. But
I would love to come.
Why don't you rather email me and let's chat about it? Because the question of where should I study, it's never a simple question. Sometimes people are just like, oh, go to this university, it's the best one. But that's not the only factor. It might depend on your situation with your family. It might depend on what city you want to live in. Might depend on financial constraints. So there's never a simple answer to that. I will say that if you want to do astronomy, you need a degree in physics or astronomy. So UCT and I guess UNISA, you can do an undergraduate in astronomy. You don't technically have to. I didn't. I did a physics degree, and then I did honors with NASP. So your undergraduate just needs to have physics. It needs to have a physics related field. You need to do some maths, and I would definitely strongly recommend doing some computer science as well. But in terms of where to study, I think maybe drop me an email and let's chat about it and see your kind of personal circumstances and see what might be the best option for you.
Okay. Yeah, because I did finish my matric, but I finished it in 2005, and my results weren't up to par. And my dad, he was like, don't worry, relax at home. We have everything. Why do you want to study further? And I had a life-altering event that happened a couple of months ago, and I realized I need to follow my dream. And my dream was always to study astronomy. So my age, I'm actually 33. So that doesn't hinder me from applying at university, right?
No, it definitely doesn't. The downside is if you want to try get a scholarship, most of them are restricted to younger people. but it definitely doesn't stop you from going to university. And, you know, certainly some of the best students that I've worked with are older students, because they know what they want. They know that this is their dream. And so they're really motivated. So if this is something you want to do, definitely go for it.
Thank you so much. I will drop you an email. You have a great evening. Thank you.
Thanks.
Asif, thank you so much for your question. All right, so I think we will wrap it up there for the evening. What I'll maybe say is I'll give it one last round and then we wrap it up. If there's any more questions, please feel free to ask your last question. Just looking for the list. I don't see any more hands up. In this case, Dr. Michelle, I'm going to say thank you so much. I mean, just by the amount of questions that we've had afterwards, we can see that we have had a really attentive crowd, and everyone really enjoyed your presentation. Thank you so much for making yourself available and attending our Cape Center meeting tonight.
That's my pleasure. And I'll just say again, I put my email address in the chat. So if anyone's got more questions, just feel free to email me. And thanks again for inviting me. It's really fun.
Thank you so much. We've had a very, very interesting evening. Thank you once again. I would like to thank the rest of the audience for attending tonight's meeting. As you may be aware, the meeting is being recorded, so I will be uploading the meeting to our Cape Center YouTube channel. We're going to formally end the meeting now, and I'm going to say thank you so much for everyone for joining. I'm going to keep the channel going a little bit so that we can all switch our videos back on and have a good chat, and you're all welcome to stay on. But thank you so much for joining us, and have a wonderful week.